Hi, this is Ryan Bell, and today I'm going to talk to you about global thresholding and uh, Otsu's method, which is basically optimum global thresholding. And I'll provide a small foundation on thresholding in general. So, thresholding essentially separates pixels of an image into classes that are distinct based on a defined threshold. So I found a program that someone made, and this is an output of that program in which you're defining a threshold of basically keeping things that are green and eliminating everything else that is not green. And so that is demonstrated in this output down here in the image. So when using threshold techniques, there are different ways of doing it. And the one that we are going to be using is a histogram. So a histogram is bimodal in the sense that it generally has objects in the foreground, and then it has a background, and those generally have different intensities. And the histogram method, or using histograms, we will analyze them by looking at like peaks, valleys, and curvatures of the histogram. And so I found this image online, but I added a little curve to it, so you can imagine it as a histogram, a curved, smooth histogram, and you can see the peaks and the valley right in the center. It's not the best, but tried to add it with the PowerPoint tool, so it's not exact, but you get the idea. And so now I'll mention what basic thresholding is. We just basically define a threshold, and in our case we're using an intensity threshold, and by defining that threshold we can classify the pixels or the outputs of f of x, y into distinct groups based on their relations to t. So you will have pixels that are more intense, maybe are greater than the threshold that you defined. So if the pixel at location x, y, the intensity is greater than t, which is your threshold, then it'll be categorized as 1. And if it's less than or equal to t, then it'll be categorized as 0. And maybe you might say that 1 is more intense and 0 is non-intense. And so there are a variety of threshold techniques, and so there's global thresholding, in which t is a constant over an entire image, and then variable thresholding, in which t is variable over the image, and subsets of that include, for example, like regional thresholding or local thresholding. And regional thresholding is when you have a variable threshold over certain areas or neighborhoods of a region. So you can have multiple thresholds based on a sampling or like a neighborhood of the image. And so an example of that would be like the average intensity in a neighborhood XY for the given image, and that'll be different for a bunch of neighborhoods all across the image. And then adaptive/dynamic thresholding is just thresholding, or it's when the threshold t depends on like spatial coordinates. So that's that. And then optimal global thresholding uses Otsu's method, and that basically you want to find an optimal threshold in which the number of misclassified pixels is minimal. So when you're classifying these pixels, there is a fair amount of error, or can be error, when classifying them. So maybe, for example, this would be probably in more complicated cases, or when the curve is a little more complicated. So if, for example, a pixel that was really intense was classified as a 0 somehow, and was classified as less than or equal to t, then that is a misclassified pixel, and so that is an error. And so the optimal threshold found through optimum global thresholding serves to minimize the error. And I will later in this video go over Otsu's method to help find that optimal threshold. First, I'll talk about multiple thresholding, and this generally defines two thresholds in which are used to partition, separate, and classify pixels within an image. So it's basically the same idea. The only difference now is that you have two thresholds instead of one. So you can have one that is like the least intense. It'll be the lowest intensity class, which is given by C in here. And then you may have your in-between, which is the medium intensity class, so to say. And then the most intense pixels will be given as A in this example. And so that would also based on what I was saying through this example, that would also mean that T1 was less than T2. Of course, the first threshold was a smaller value than the second one. And so some examples of this, just some histograms or graphs, images that I found that I thought were interesting. So the first one shows there's a single threshold. This is from the book, actually, so you can find this figure in the book. And it just shows a single threshold, your average, your typical case in which you have a single threshold. And then the second one shows a case for multiple thresholds, or as they say here, dual thresholds, in which there's two of them. So we've got, for example, C here. Maybe that would be less than T1. Oops. So less than or equal to T1 right there. And then our B values are in between T1 and T2, as shown here. And then our A values are greater than T2. So there's that. And the bottom image I kind of just found online, and I thought it was interesting. It was just an interesting interpretation or illustration of the idea behind it. It's so if you consider A and C as thresholds as well, then you can also see, like, maybe on the left there's the foreground, and then in between A and C, or it's kind of an in-between area, and then to the right of C is a background, the background pixel elements. And so some factors when choosing a threshold. So some of the factors that make a big difference when choosing one include like the separation between the peaks. So how wide are the peaks? Like this one has on the bottom has a pretty good distance. It's not too like close together. The noise content in the image, that can make it a little more challenging to choose a good threshold. The relative size of the objects and the backgrounds, the uniformity of illumination or light, and the uniformity of the reflectance. And so now I'll talk about just a more simpler or an automated threshold estimation algorithm. So this is used commonly for it was in the section for global thresholding, and so you would select threshold T, and then as it says here, segment the image using T, and by segmenting the image, it'll produce two groups of pixels, G1 and G2, and that equation there, 10.3-1, is just separating. It's just separating the pixels based on like what I had, similar to this here. So it separates them into two classes. And so you do that, and then you compute the average mean intensity values M1 and M2 for the pixels in both of those classes, G1 and D2. So it got a little messy here because I wanted to include the formulas in the slides so it was all easily accessible and you can see it all here at once. So M1 and M2, those means are listed here, and the formulas are listed here. So there's that, and then you compute a new threshold value, T equals 1/2 times the quantity M1 plus M2, or the sum M1 plus M2, and then you will repeat those steps, going from 2 to 4 in a loop until the difference between the newly computed threshold value and the previous one is smaller than the predefined parameter delta t. So delta t you can define basically as how much you want the threshold to be like perfect or accurate. So you can define it as 0, for example, so that the new threshold minus the previous threshold must equal 0, and it'll keep going until then. And this whole iterative algorithm works best when there exists like a clear value between the modes of the histogram. And so now I'll start talking about optimal global thresholding, and this is commonly done through Otsu's method, and this will take an m by n image histogram with L intensity levels ranging from 0 to L minus 1 in this case, and n sub I numbers of pixel intensities. And the total number of pixels also, mn, is given by the sum from I equals 0 to L minus 1 of n sub I. And then the normalized histogram is equal to the sum of p sub I equals 0, L to L minus 1, which is also equal to 1. And those formulas are written there. And so to make things a little simpler, I chose to just, from this point, I'm gonna reference another PowerPoint that I found online, because there are a lot of equations and formulas, so I didn't see any reason to really rewrite all of those formulas or copy all of that, because that would just take a lot of time and seemed unnecessary. So let me go to that right now. And here we are. So optimum global thresholding. So using Otsu's method, we want to maximize the between class variance. And I'll explain what that is in a moment, or in a bit later. So let's see. So we want to define a threshold level t equals k, and we have the two classes here as shown in this slide, given by C1 and C2. And so C1 is contained in it's the threshold in which it has the pixels of intensity like 0 to threshold k. So the pixels which their intensities are less than k, and then or less than or equal to k. And then C2 has the pixel intensities that are greater than or equal to k plus, or they're between k plus 1, L minus 1, which is shown here. And so the mean intensity of the classes C1 and C2 are shown on the left here, and there's a little derivation here with quote-unquote Bayes formula. And so that's just a little conditional probability. And that gets you to this formula on the right. And then if you want to calculate the global mean, then that formula is also listed here. So basically, this is kind of just an index or a listing of all the formulas that are useful in finding an optimum global threshold, really, through Otsu's method. That's why I thought this PowerPoint was useful. So they've got the separability measure, global variance, and like I said, I would mention what the between class variance is. And so one second. The between class variance is basically a measure of the separability between classes. So it's a measure of if it can, or how well it can separate into the class 1 or the class 2 based on like those inequalities. So that helps in dealing with like the error in which there are, you know, misplaced pixel elements, and it helps in going through the algorithm to minimize the misplaced pixel elements. So so the separability, to the larger the hold on one sec. The bigger the two means are, so the more distinct they are, the larger the variance in the separability, or sorry, in the between class variance. So if you have bigger means, then the more distinct they are, and then or what I mean is the difference. The bigger the difference is, the farther the M1 and M2 are, the bigger the between class variance is going to be. And so here's an overview of the algorithm. We want to compute the normalized histogram PI, and then compute P1 of K, and you'll also probably want P2 of K, which is shown up there, how to get that. I believe I have it in my PowerPoint. You'll compute M of K, so you'll find the cumulative mean, and then you'll want the global mean, and you'll want between class variance, and eventually, after all that, you'll be able to get to Otsu's threshold K star, which is just the max of the between class variance. And so, given a parameter K, of course. And then after that, once you compute, then you can just compute the separability measure. And that's it for the optimum global thresholding. And so, let's see. I also have a summary here. This is essentially the summary from the book. So, but it also I thought that other one was easier to look at, since it has all the formulas there. This has a few references which aren't in the PowerPoint. And so, just in case you need to know the website for this, let me see. So if you type in basic global thresholding, it'll probably be the third, it should be the third one that pops up, or so. I believe it's this one. Nope. Nope, not that one. Sorry, it was the first one. It has an 8 there. So if you need to find that PowerPoint, which has a lot of useful information, I'd recommend going to the first one. So you just type in basic global thresholding, and it should be the first one, which is a PDF, and it has the number 8 there in a bracket. So you click that, and you'll be there. This is it. And so now I'm just going to show you an application of Otsu's method once it's been applied. And this one's from the book, so you can see the original image here, the histogram with the peaks and the valleys and whatnot. And then this is using the basic global algorithm, which is the one I mentioned up here. And after that, you have this one, which is the result of using Otsu's method, which is a lot nicer. You've got a clear cut of the image, the original image. You get a clear threshold, and so that's why it's known as the optimal global threshold, because compared to the other ones, it looks the best, and it's more detailed, the algorithm to find the optimal threshold. And so that's it. If you have any questions, let me know.